Hello guys, this is Paul McWhorter from TopTechBoy.com, and we're here today with lesson number 7 in our new series of tutorials on how to build a non-axis inertial measurement system. I will need you to pour yourself an enormous mug of iced coffee, and I will need you to get your gear and code out from where we left off in lesson number 6. Now, if you haven't gone through the earlier lessons, you need to go back and take those and get caught up, because this is just kind of starting out where we left off in lesson number 6. Just as a reminder, we are using the most excellent Adafruit BNO055 inertial measurement sensor, and we have it connected to an Arduino Nano. If you don't have this hardware, look in the description down below. There's links. On a project like this, we really need to be working on identical hardware. So you can get your hardware down below, and then also you need to get the code. We're starting with the code where we left off in lesson number 6, and you can get that code by going to www.toptechboy.com, and we'll switch over there. You just search for non-axis IMU lesson number 6, and then once you get to this page, you can scroll down and you see that we have this nice convenient place you can get the code. Hopefully you've developed this code along with us, but if you want to catch up, you can just go get the code there. Now, just as a quick reminder of where we left off in the earlier lesson, we are taking the data from the x accelerometer, the y accelerometer, and the z accelerometer, and then we're doing some calculations based on trigonometry to approximate tilt. And we have this tilt angle theta, and let me back off a little bit so you get a little bit better view. Let me help you get a focus. Okay, we have this theta, which is sort of like the nose of the airplane coming up and down the pitch, and you can see that as we pitch, you see a nice signal in theta, very well behaved, come down, nose down, it goes negative. We're going to roll to the right, and then our phi comes up, and then we're going to roll to the left, and our phi goes negative. And so we've got some kind of nice approximations for pitch and roll of our device. Okay, but what was the problem? The problem is that these accelerometers really are accelerometers, and if you have vibration, you're going to start seeing a signal where you misinterpret that vibration data as changes in tilt. And so your homework assignment in lesson number 6 was to go away and see if you could come up with a way to try to deal with this vibration problem. Because imagine, like, if you put this on a Jeep or a off-road vehicle and it's sitting there and you want to sort of measure at what angle you are from the horizon in your vehicle, but when the motor turns on, all of a sudden you start seeing a signal like that, which is as big or bigger than the signal that you're trying to measure of tilt. So how would you go about doing that? Well, leave me a comment down below. Was anybody able to figure this out, or did anybody have any insight as far as how to approach this problem? The answer really gets to what the title of this lesson is, and that is understanding low-pass filters. And kind of like low-pass, high-pass. Low-pass means low frequency, and pass means we want to pass the low-frequency data. And low frequency you can kind of think is slow. So I'm starting to go up a hill, and then I level off, and then I go down a hill, and then I go over a rock. You see, that is low-frequency data. What is this? This is high frequency data. So low pass means I want to filter out this high frequency data. Kind of like the way you could think of it is that when do you trust your sensor? You trust your sensor with slow moving signals. If you see something change quickly, you tend to want to discount and not trust that. And so let me switch over and see if I can start doing a little bit of math, and then maybe we can go over, well, not maybe, certainly we will go over and then start coding it. So I need a better overhead view here. Okay, I think that looks pretty good. Get this out of the way. And let's remember that where we ended up earlier, we had a theta and we had a phi, okay? And we got this was from the accelerometer. Okay, and the way we're doing it now, just whatever the accelerometer says, we trust. But now with a low pass filter, and what we're going to do is let's call this theta measured. Okay, theta sub m and phi sub m. This is just what we measure it. We just dumbly go out and take a reading from the accelerometer and turn it into tilt. We'll call that the measured value and the phi measured value. Those come from the acceleration. Now we want a concept of a filtered value. Okay, so the theta f, what we've got to also see as we filter it, we got to remember what it was the time before, because we don't want to trust quick changes. And if we're going to kind of keep track of whether the change was quick or not, we've got to know where it is now, and we've got to know where it was before. So we're going to have this idea of the theta filtered the old value and the theta filtered the new value. Okay, and so let's just jump in with the math and say, what would the theta filtered new value be? Well, it's going to be equal to the theta filtered old value times some parameter plus the theta measured times, let's call this P1, and then let's call this P2. And then what you have to see is that P1 plus P2 has to equal 1. So if you see our filtered value for tilt is going to be partially just taking what the old number was and partially taking what the new number is. And then this plus this has to equal 1. Well, what we can see is that for the accelerometer, we really, if it comes up and all of a sudden just out of nowhere I have a 45-degree tilt, I don't really want to trust that because I know it could be vibration. So let's say I might make this, I only want to trust this 10%, I might make this factor 0.1. Well, then what would P1 be? 0.9. Okay, so I'm not going to believe that accelerometer just because it comes up and tells me that it's 45 degrees out of nowhere. I'm just going to give that a 10% weight. All right, and that means a 90% weight is I'm just going to believe what it was before. Well, think about it. If all of a sudden it was a real tilt, then over a couple of measurements, it's going to come up to what it really was. But if this point was just noise, then instead of getting this huge noise signal, you're just going to get a small noise signal like that. Does this make sense? I hope it does. So then what I'm going to have is I'm going to have phi sub m is the measurement off the accelerometer. Then the new filtered value is the old filtered value times a parameter plus the measured value times a parameter. And then at the bottom of the loop, what you have to see is that theta f old is equal to theta f new. So you got to kind of, the value that was new this time, next time around, it's going to become the old value. All right, let's get out that code and let's see if we can start playing with this and make this work. Okay, let me go to a code view and let me get this back over here, get some things put together, and let's see if we can start coding. Okay, so I need to get this where I can see it. Hopefully you guys are here, and let's just do a little bookkeeping. What we said was we're going to change some of these. We're going to change some of these. So this theta, let's call it theta measured. I'll put a large M, theta measured and phi measured. Okay, and then I'm going to also need the theta filtered old, and I'm going to need theta filtered new, and then I'm going to need, remember the then the fees as well, so I'm going to need fee filtered old, and I'm going to need fee filtered new. Does that make sense? Because we have these new variables, we've got to declare them. All right, so now where we come down here and we start making some measurements. So remember, we still have all this calibration stuff in here. It is here in our void loop. This is that calibration code, and then this IMU vector 3. Remember, that is the that command that actually goes and gets the acceleration vector. It returns the acceleration in the x, the acceleration in the y, and the acceleration in the z. Now this theta that we are taking directly off of the accelerometer, that is going to become what? The theta measured. This isn't the filtered, this is just the theta measured, and now this one is the phi measured. Now what do I need to do? I need to calculate, and if I'm going to do this, I probably need to set all these things to, I need to set these to 0, the old values, because the first time through the loop the old value isn't going to have a value, so I need to give it one so that the program doesn't crash. Okay, so now I am going to calculate the phi, and this time filtered new. And let me make sure I'm doing my variables right. Phi filtered new. And I'm sorry you can't see those whole lines, but I'm setting my font big enough so that you can see me typing, and you've got this code in your own thing if you got it from lesson number 6. So phi filtered new, what did we say that was going to be? Well, we're going to start and we're going to say that it's equal to 0.9 times phi filtered old, because we want to trust the old value. We don't want to trust the new value. The accelerometer is not trustworthy. Plus, and then we're going to give a 10% weight, 0.1, to this phi measured. Okay, then theta filtered new is going to be kind of the same thing, 0.9 times theta filtered old plus 0.1 theta filtered new, or theta measured. I'm sorry, theta measured. So we're using the new value is a combination of the old value and the fresh data that we just got off the accelerometer. Okay, so now we better do a little bookkeeping, and what we were printing here earlier was theta. Well, let's just make that theta m and phi m. Okay, but we want to print these new filtered values because we want to kind of compare the filtered values to the unfiltered values to see if our filter has done anything. So now let's do a serial.print. What do I need? I need to put another comma in, and serial.print. And what do I need to put here? I'm going to do theta filtered new, because that's what we just calculated, and serial.print, and we're going to do a comma, and then do a serial.print ln, and now we're going to print phi filtered new. All right. And what do we do on the last one for the serial monitor? We make the last one that we print LN. And so before, I think this was the last one and I had an LN there. Well, now I just put the LN on the last one. Okay, so we will need you to hold your breath as we try to download this program. There is no telling how many mistakes I made. Did I put my colons up here? That's usually, semicolons, that's usually what I forget. Yeah, it looks like I did. Hold your breath. Oh, darn it. Darn it. Oh, my goodness. Oh, disaster. What did I do here? Theta F new is equal to theta F old plus 0.1 times. Okay, so let's see. All right, let's try to download again. This time, hold your breath. Oh, again. I know what it is this time. I know what it is this time. Remember over on our serial monitor, we're still running our serial monitor. I need to turn that off. Okay, turning the serial monitor off. I just selected a different port. Now that should work. Hold your breath. Yes, yes. Download, download. Oh, boom. There we go. There we go. Yes, it is working. Life is good. Life is good. It is working. Okay, so let's go back here, and we got it to download. So now what we want to do is we want to go over and we are going to look at the serial plotter again. And so let me call up the serial plotter. And the first thing is we plotted two more channels, two more data channels. And so we need to come over here to our data format, and besides the 9 that we were already printing, now we've got 10, 11. And then we need to come over here to plot, and we need to give those better names. This was going to be theta M, or theta filtered. And then this is going to be phi filtered. Okay, phi filtered. All right, so now let's look at those. We probably, yeah, let's look at those things now. And so I'm going to come back up here and I'm going to turn my COM port back on. Okay, so hoping that it comes to life. There, it comes to life. Now let's tilt. And then let's see. Okay, did not really do anything at all. So we made a mistake in our low pass filter there somewhere. So we have to take the happy little clouds away because this is not working. All right, let's go back to our code and see what is happening. Sorry guys, it takes me a second to find my code. Okay, there it is. Okay, let's look at those calculations that we did. We go out, we get the reading from the IMU, we calculate theta M, we calculate phi M, then we say phi of F new is equal to the old value plus 0.1 times the measured value, and then 0.9 times theta old, theta filter old. Oh, I know what we did. After we get to the bottom of the loop, we've got to put away, right? What did I say that we had to do? We have to say that phi filtered old is going to be equal to phi filtered new. What is this saying? Is that the new value, when you go back again in the loop, it becomes the old value. Okay, so the new value becomes the old value, and sort of same thing, theta F old is equal to theta F new. All right. I believe that should fix it. Please hold your breath. Oh, darn it. How could that? Oh, forgot to turn the serial port off. I keep doing that, guys. I am so sorry. We got to remember that we have to turn this off or we can't download it. Only one thing at a time can be touching that serial monitor or serial port. All right, so now let's try. Let's come back over here, and now let's try to download it. Yes, yes, yes. Download, download, download. Boom. Okay, it downloaded. So now we are going to go back now and look at our serial monitor, our serial plotter. Let me call that up. Okay, and so now we're going to turn it back on up here by selecting COM5 and then clicking open, and we hope it comes to life. Okay, now it comes to life, and you can see that I'm printing theta and phi and theta filtered and phi filtered. Okay, so let's see what happens if I put a little bit of tilt on this. Okay, now what you see is, look at what's happening. Okay, do you see what's happening? The filtered value is becoming slower. Okay, they both get to the same value, but the unfiltered just pops right up there. Why does it pop up there? Because it always trusts the accelerometer. The filtered data doesn't always trust the accelerometer. Okay, so now let's see, same thing here. On pitch, the unfiltered moves quickly, the filtered moves slower. But let's verify they should get to the same value. So let's just kind of tilt it here. And it takes it a little bit longer to get up there, but they get to the same value. Okay, now let's do the vibration test. Okay, in that case, I'm just going to look at one value. I'm going to look over here. Let's just look at theta. Okay, let's look at theta and theta filtered. All right. Okay, can you see the difference between the unfiltered and the filtered? Okay. The unfiltered is the bright green, and do you see how much noise there is? And do you see how much of that noise that we have been able to take out by putting in this filter? But now if you look, you see the unfiltered is much more responsive, but overall we're getting a lot better data, a lot cleaner data by applying this low-pass filter. All right, let's look at the, those were the thetas. Let's look at the phis, and so I'm going to turn on phi, and then I'm going to turn on phi filtered, and I believe that should be in this direction. Same thing, okay, same thing. What you can see is that the unfiltered is much more responsive, okay, but the unfiltered is much more susceptible to noise. And so let's turn the unfiltered off, and let's just look at the two filtered values, and let's see if we've been able to compensate for vibration. Okay, I would say that's not very much vibration, right? I think that we've done a good job. It looks like it's just a few degrees now. Okay, so what have we learned today? We have learned about a low-pass filter. Okay, we have learned about a low-pass filter. You use low-pass filters in situations where filters or signals are noisy, and if you have a bunch of noise, you build one of these mathematical low-pass filters and you can filter it out. What is the implication of doing that? Well, you make your sensor a little bit more sluggish. All right, you make your sensor a little bit more sluggish, but you get much more stable results. So let's play around with those parameters a little bit. Okay, let's come back over here. And do you remember where we were setting those two values? And I gave like 0.9 to the old value and 0.1 to the measured value. What if we wanted to make this a little bit more responsive? Well, we could make this 0.75 and we could make this 0.25. So I'm going to give a little bit more weight to that new data point, 0.75 and 0.25. Okay, now I am going to remember to turn my serial port off this time, and then I am going to come back and I'm going to try to download it. All right, and now let's go back to our serial monitor view. Okay, so this time I am giving more credit to the new measurement. Okay, so if you look at this, got to turn it back on. Okay, COM5 and open. Waiting for, okay, now it's come back to life. Now if I tilt, I got to turn the filtered on and the unfiltered. So I'm looking at tilt, theta, filtered and unfiltered. All right. Now look how much quicker it was to respond. Can you see how much quicker it was to respond? That dark green is keeping up with the light green a whole lot better. What was the cost of that? Now the dark green has more noise. Okay, the dark green has more noise. So if I want it to be snappy and responsive, I can give more credit to the new measurement. Okay, but the cost that comes with that is you're filtering out less of the noise. Let's go the other way. Let's see if we can get rid of all the noise. Okay, so we'll go back to our code view. So how would we try to filter out all of the noise? Let's make this 99%, 99, and this one 0.01, 0.01. And then we will download this. What did I do? Oh, 2 points. Did you guys see that? Okay, now let's download this. I am sure that is going to work. We'll come back over to our serial monitor. Serial plotter, we are going to put it back on COM5. And yours might not be COM5, right? That's just mine because that's what my Arduino is on, COM5. And let's see if we can get this thing to come open, come alive. Okay, so now let's look at some vibration. Okay, do you see that dark green? Man, do you see I have gotten rid of all of it. It is just dead steady. Okay, tell me what price I'm going to pay for this level of, you see the light green is the unfiltered and the dark green you cannot perceive any noise at all in it. But what price am I going to pay for that? Right? What price am I going to pay? Do you see how slow it is now? It'll eventually get up there. Okay, it'll eventually get up there. But it is really, really slow. Okay, so that probably is too slow to really be useful. And so what I'm going to kind of try here is I'm going to try like 95% and 5%, 95% and 5%, and then we're going to download it. Oh, what is wrong with you, you aggravating thing? I hate it when that happens. Crashed and burned. What did we make? You know what we did? We forgot to turn our serial port off. So let me come back over here and let me turn this to COM1. Okay, and then we will come back over here and we will download it again. Guys, this would be a lot easier if I had someone helping me with the production, but I'm having to think about the project, I'm having to do the project, I'm having to make sure that I can see the right window and make sure you see the right window. So if I'm a little sluggish sometimes, there's a lot that is going on behind the scenes here. Okay, so that looks good. Let's come back here to our serial plotter, and then let's turn it on. Serial plotter. Okay, so we're giving 5% weight to the new measurements and 95 to the old measurements. So let's see. I would say that the noise filtering is pretty good. Do you see that dark green isn't moving much now? Let's see how sluggish it is. It is a little bit sluggish, but if you were thinking about this for like a vehicle inclination or something like that, I think that this is probably acceptable. It would sort of depend on your specific application. Okay, guys, with a low pass filter, we have kind of done pretty good as far as getting rid of that noise. But at this point, what is the limitation that we have at this point? The limitation is that we're up against this kind of fundamental trade-off between responsiveness and being snappy versus having a problem from noise. And so what your assignment for next week is, which will be lesson number 8, how can you incorporate something new? How can you add something to this where you don't have to make such a painful trade-off? Is there a way that you can get something that's quicker, a little bit quicker, okay, without reintroducing the noise? That is your assignment for next week. You guys, if you like this, think about giving us a thumbs up. Think about subscribing to the channel. Would love it if you guys would share this with other people. Think about putting it on your social media. Really appreciate my audience. Appreciate you guys tuning in every week. Love to hear your feedback back in the comments. Paul McWhorter from TopTechBoy.com. I will talk to you guys later.